After an introduction to fundamental and derived dimensions of space, we can start seeing the basics of how dimensional analysis helps us describe the links between data and the real world. Our abstract philosophical definition of datum was focused on how data lends objectivity to the practice of science. But the dimensional perspective suggests that maybe we can find a more specific definition of datum when applied to quantitative science. The quantitative definition for a datum that I like is an evaluation of a property that describes an entity within a given dimensional reference frame. The idea of dimensional analysis is to give us an unambiguous algebraic language to use when explaining to other scientists what can be interpreted from a given value we have measured. We all know that units are important to knowing the meaning of a number, evaluating a variable. But while the scale for the number is important to using it in calculations, the dimensional context hinted by the units are even more important to fundamental agreement on how numbers should be interpreted. I suggest that relying on units alone to provide dimensional context is an ambiguous practice, and the formalizations of dimensional analysis are worth learning how to use. A more general application of dimensional analysis requires that we describe more properties of nature than just space. Let's work our way through the fundamental table of dimensions as suggested by the International System of Units, which we usually just abbreviate to SI units. A categorization and standardization of units across multiple cultures inherently requires dimensional thinking based on the most fundamental properties of nature that we all understand. So it is logical that the basis for standardization of units is inherently built from a definition of fundamental dimensions. We've already talked about the fundamental dimensions of length, so I've already revealed that row from the table. Many different variables may be used to represent length, as demonstrated by our use of x, y, and z to represent lengths in orthogonal Cartesian directions. Ultimately, the goal of SI is to define a base unit for each fundamental dimension, so the base unit for length in the SI system is the meter. As made famous by Albert Einstein, characterizing movement in space inherently requires thinking about the dimension of time, which is symbolized with a capital T. More often than not, time will be represented as a variable using a lowercase t. Time is one of those concepts that everybody understands abstractly, but the nature of time is very difficult to describe directly. I like to think about time as the dimension of causality. One inarguable fact is that those of us operating in Earth's gravitational field are all experiencing the same rate of cause and effect. The concept of time allows us to agree on a common way to measure the pace of a resulting sequence of events. Einstein famously showed us that the fundamental rate of time and causality actually changes with your frame of reference. But earthbound environmental scientists typically do not have to deal with meaningful variation in the pace of time in their calculations. The international community has agreed on the second as the base unit for the dimension of time. Speaking of gravity, another inarguable fact is that we all see the same effect of the stuff we call matter on spacetime. The degree of this effect is conceptualized as the dimension we call mass, which has the symbol of a capital M. The magnitude of the effect of mass on spacetime is proportional to the magnitude of the apparent force we call gravity. Though I think it is pretty well established at this point that gravity is actually a bending of spacetime that only has a similar effect as a force. The proportionality of mass with the effect of gravity gives us the ability to measure either based on the effect of Earth's mass on a given amount of matter. The international community has agreed that the base unit for mass should be the kilogram. While we often quantify an amount of matter relative to its gravitational effect, few scientists would argue against the idea that matter is made of bits of stuff we call molecules. So another way we talk about the amount of matter is simply by counting those bits, where the dimensions of this count are symbolized with a capital N. When we count in multiples of Avogadro's number, this count has units of moles, which is the international base unit for an amount of the substance. I would argue that counts are not limited to an amount of substance, and it is possible to have the dimensions of count applied to conceptual entities as well. In terms of base dimensions, I'm not sure amount of substance is a general enough descriptor for the concept of a count, but it does provide a useful example. The need to predict the inarguable effects of matter on other nearby matter begins to highlight the need for dimensions related to energy. As we will see later, Newton's definition of energy does not require a fundamental dimension and can be derived only from the fundamental dimensions of mass, length, and time. However, thinking about the thermodynamic energy content of matter starts to evoke notions of properties like temperature, based on the idea that we all fundamentally know the difference between stuff that is hot and stuff that is cold. The dimension of temperature is symbolized with a capital Greek letter theta, probably because a capital Latin T was already taken by time. Or perhaps because a capital Latin T is used as a variable for temperature. This potential confusion among symbols used for variables, dimensions, and units is why the best practice is to include square brackets around dimensions to differentiate them from units and variables. The SI unit for temperature is a Kelvin, where 1 Kelvin is conveniently the same difference in temperature as 1 Celsius degree. A couple more dimensions we will not focus on now include electrical current and light intensity. The dimensions of current are symbolized with an I, and the SI base unit is the ampere. We will talk later in class about current being derived conceptually from a count of electrical charges per time. We will not be using light intensity in this class, but the dimensionality of J should not be confused with the unit of joules of energy. Again, the square brackets help to differentiate a symbol that is used both for dimensions and for units. Luminous intensity is ultimately a type of angular energy flux with a base unit of candela, which would be joules per steradian per second, where a steradian is a kind of a 3D version of an angle. There are nuances here regarding what constitutes a fundamental versus a derived dimension. You might argue that a current is actually a derived dimension, and luminous intensity is almost certainly a derived dimension. Ultimately, the distinction between fundamental versus derived dimensions is not that critical, as long as the element of nature being described is clear. Let's review a couple more dimensions that may be argued as being fundamental, though they have elements of derivation. We have already talked about the derived spatial dimensions of area and volume. These are so commonly used in describing space that we seldom say length squared or length cubed when using these dimensions in a sentence, even when describing them in dimensional analysis. While the symbol and derived dimension is length squared, we usually just say a corresponding variable has fundamental dimensions of area. This brings up another potential point of confusion in inferring dimensions from units. Dimensions like area are commonly depicted in square units of length, like square inches or square meters. However, area may also be specified in absolute units, like hectares or acres, which do not directly evoke the squared length nature of the dimension. Volume might be specified in a large collection of absolute units, like gallons, liters, teaspoons, cups, etc., again not hinting at the cubed length nature of the inherent dimensions of the variable. Where absolute units are applied to a derived dimension, remembering the dimensions based on applied unit requires a bit more memorization. Finally, many of the more transferable or comparable properties across many different types of systems are characterized with dimensionless variables. Dimensionless is a derived dimension in the sense that it arises from dimensionality of a ratio that divides out to unity. We have already viewed a dimensionless property of circles that we call pi. Fractions of a whole is another example of a common application of dimensionless ratios. Just because a variable is dimensionless does not mean that it does not have units. For example, we very commonly refer to fractions of a whole in units of percent, which is a unit representing the ratio of a given count to 100 count of the same thing. We can use a similar principle as pi to think about the dimensionality of an angle represented by units of radians. A radian is characterized by the distance along an arc of a circle cut off by 2 radii of that circle at a given angle. The distance along this arc has dimensions of length. To normalize this notion of an angle to any size circle, we normalize the length of this arc to the radius of the circle, yielding the derived dimensions of unity, or a dimensionless number. You might also remember the dimensions of radians more specifically as a length per length, to remind you of the nature of the property being measured. To solidify your understanding of the radian, you might start with the definition of pi and convince yourself why pi radians make sense as the angle that divides the circle in half.